All right, let's dive into this really fascinating world. A world where the exact same calculation can give you totally different answers, and how engineers came up with a seriously clever way to force them to be perfect.
So, let me start with a question that, seems to break one of the most basic rules of math we all learned in grade school. But what if I told you that in the world of computers, this isn't just some hypothetical question? It's a real, frustrating problem they deal with every single day.
Yeah, this is no trick. It's a core challenge in parallel computing. It happens on all the powerful devices like GPUs that are really the backbone of, well, everything, from training AI models to running those incredibly complex physics simulations in the video games we play.
So here's the deal. Computers can't actually store numbers with infinite precision. It's just not possible. They use a system called floating point arithmetic, which is an approximation, and every single time they do a calculation, there's a tiny, tiny rounding error. Now, when you add up millions of these numbers, the order you add them in, well, that changes how all those tiny errors pile up, and you end up with a slightly different final answer.
Think about it like this. A GPU is like a giant stadium with thousands of runners, we call them threads, all sprinting to update a single scoreboard. The problem is, you have zero control over who gets there first. The finishing order is determined by really complex hardware stuff, the GPU's own internal traffic management system. And that means the sequence of additions is basically random every single time you run the program.
What's so interesting here is how this breaks down the four horsemen of this numerical chaos. You've got your basic rounding errors from just not having enough bits. You have the non-associativity we just talked about. Then there's the unpredictable GPU scheduling. And then there's this really sneaky one called absorption. That's where adding a really tiny number to a huge number can just make the tiny number vanish. Poof. Like it was never even there.
Okay, so if you're a developer, your first instinct might be to reach for a standard tool called an atomic operation. You'd think it's designed for exactly this kind of parallel traffic jam, right? But, as we're about to see, it's actually the worst thing you can do if you want to guarantee a correct answer.
And this slide just nails the difference. An atomic operation, something like atomicAdd, it's basically a traffic cop for your computer's memory. It makes sure only one thread writes to a memory location at a time so you don't get data corruption. It solves the race condition problem, but it does absolutely nothing to control the order in which those threads show up to the party. So it guarantees your memory stays consistent, but it completely fails to give you numerical reproducibility.
This is absolutely wild. It means the final bit-for-bit result of your calculation can literally depend on how hot your GPU is running at that exact microsecond, or maybe what other programs you have running in the background. Your result is no longer just a function of your inputs, it's a function of the chaotic physical state of your machine.
So this all leads us to two very different ideas of what correct means. There's weak reproducibility, which means you might get the same answer if you run the same code on the same machine with the exact same settings every time. But if you change anything, a different GPU, a new driver, even the number of threads, it all breaks. And then there's strong reproducibility. This is the gold standard, the exact same bitwise result every single time on any machine, anywhere. That's what we're aiming for.
So how in the world do we get to that gold standard? Well, it turns out we have to do something that sounds crazy. We have to temporarily stop using floating point math entirely. We need a completely different, much bigger bucket to do our adding in.
Say hello to the superaccumulator. Instead of a floating point number, which is always just an approximation, this thing is a massive fixed point buffer. We're talking hundreds of bits wide. The best way to think of it is like a hugely detailed accounting ledger, with a separate column for every possible decimal place, making absolutely sure that no precision is ever lost when you add things up. And this is the aha moment. When you convert the numbers into this fixed point format, addition becomes exact again. It's like doing math on paper. It's perfectly associative. Suddenly, it doesn't matter what order those thousands of GPU threads arrive in. A plus B plus C is now exactly the same as A plus B plus C. Problem solved. Okay, but how does this beautiful, elegant concept actually get put into practice efficiently? I mean, in the real world. Modern libraries like NVIDIA's CCACL or other projects like XBBLS don't just use one single giant accumulator. No, they use a really clever multi-level strategy.
The whole process is kind of like sorting a giant pile of cash. First, you pull out the really big bills, the large numbers, and you handle those separately. Then, you sort all the rest of the numbers into different bins based on their magnitude. Like putting all the 20s in one drawer and all the ones in another.
You sum up each drawer perfectly, and then at the very end, you merge all those totals together to get one final bit-perfect result.
So the really crucial point here is that this method gives you bitwise identical results across totally different types of hardware. You could run the same calculation on a monster NVIDIA H100 in a data center and on a tiny low-power ARM Neon processor inside a drone, and you will get the exact same answer. We are talking so identical that a cryptographic hash of the two results would match perfectly, down to the very last bit.
Okay, so why? Why go to all of this incredible trouble? Because for a huge number of industries, getting an answer that's pretty close is exactly the same as getting a wrong answer. And a wrong answer, well, it can be absolutely disastrous. This quote from the research really just hits home. I mean, think about it. When you're talking about the safety of a new building or the results of a billion-dollar financial simulation, everybody involved needs to be able to run the numbers and get the exact same result to agree. When safety and serious money are on the line, every single bit matters.
Now let's get practical for a second. This is a nightmare every single developer has faced. If a bug only shows up one time out of a million runs because of some random floating point drift, how are you ever supposed to find it and fix it? For debugging really complex simulations, like in game physics or scientific computing, reproducibility isn't some nice-to-have luxury. It's an absolute necessity.
What's really amazing here is just the sheer breadth of fields that absolutely depend on this technology. We're talking aerospace systems that need certification for flight safety. We're talking automotive systems that have to comply with functional safety standards, high-frequency trading platforms that require auditable bit-exact trails for compliance. And yeah, it's even critical for cross-platform video games just to make sure the physics are fair and totally consistent for every single player.
And that's really the bottom line, isn't it? By using these advanced techniques, we can take the chaotic, unpredictable nature of massively parallel hardware, and we can tame it. We can turn it into a perfectly precise, totally reliable, and completely trustworthy mathematical instrument.
And that leaves us with one last provocative thought. For decades, we've had to design our code to account for the tiny, random errors of the machine itself. But as our tools become this good, this perfect, we can't really blame the hardware for inconsistent results anymore, can we? The focus shifts entirely back to the logic of the programmer, to the correctness of the algorithm itself. The responsibility becomes ours and ours alone.